And we are back. Nice to see you again. We just heard from Jan Toschke at Shell about how the company is approaching the energy transition. Well, now we are going to talk about how we will power the vehicles of the future on a large scale. Let's hear now from Dr. Robert Kohrs, the department head for Smart Grids, Division Energy, Technologies and Systems at the Fraunhofer Institute for Solar Energy Systems. Now, that's Europe's largest solar research institute. We are now going live to Freiburg, Germany. Welcome, Robert.
Yeah, thanks a lot for the nice introduction and good morning, everybody. Thanks for the invitation to present the topics of my work here at Fraunhofer ISE in Freiburg. Well, the title of my talk is Smart Grids that Power Our Cars. So we talk about smart, we talk about grids, and we talk about power. So let's define power first. In a technical context, we consider power and energy. Both units are relevant. Energy is, as you should know, the sum of power over time. So easy spoke. Just to give you a feeling about the dimensions we are facing, I made some very basic assumptions for the future in Germany. So these are all like assumptions, mean values. So if you consider like 40 million cars in Germany with a mean yearly mileage of around 14,000 kilometers a year and 18 kilowatt hours for 100 kilometers, we have in some like energy consumption of like 100 terawatt hours a year. To give that, give you a feeling, the total electrical energy in Germany 2 years ago was around 500 terawatt hours. So the additional electrical energy for future electrical vehicles is significant. It's around 20% of the total electricity consumption in Germany. If you look at the storage potential of cars, then we just say it's like 20 kilowatt hours in a battery free for storage, and 40 million cars, we have around 800 gigawatt hours. And the total electrical energy a day is around twice that value. So it's a very basic assumption. Storage is very important in future to use also the storage of the cars, but as a seasonal storage, cars will not work out. So power is the current value. Let's say it's the speed of charging. Again, using easy assumptions, we see that the power available, that means the power connected to the grid, is a factor of 5 to 10 times higher than the usual power in Germany today. So there are different charging stations, different charging power, ranging from very few kilowatts for slow charging up to high values of several hundred kilowatts for quick chargers. And these assumptions show that the peak power, if all cars are connected and are charging, is way much higher than that what we see at the system today. So as a first conclusion, we see that in grid context, power is a much bigger challenge and has higher business potentials on the other side as energy. Transforming the power system, climate change requires the total reduction of fossil fuels to zero. That's should everybody know. The electrification of mobility, on the other hand, needs renewable energies. So that is important to know. And if we go in that direction, not only in terms of transport sector, but in all the sectors, we have like a roadmap of transformation. You see here on that slide that we defined like 4 phases of energy transition. We are now in the second phase, in the middle of the second, and That means we have already developed the funding, the basic technologies like renewable generation. We are now in the phase of system integration. That means bringing flexibility into the system, bringing all the sectors together, connecting the different devices and bringing renewables in all sectors. And the following phase is then going, having the goal to totally reduce the fossil fuels. So at the moment we are having the challenge to bring flexibility in the game and storage. So just to show you what power grids means, in Germany we have the goal to build up a very decentralized system. In other countries it's more centralized, but that doesn't matter at all. We are facing fundamental change in the grid topologies and the grid design. Regional and local distribution of generation affects the grid capacities. So we have in the lower power, so we have different power levels for transport grids and distribution grids. And on the household level, we have low voltage grids. And on that low voltage level, we face massive changes. So we have a lot of new consumers that are new in the electricity sector, so like heating, like cars. This yields in a higher load, new load profiles, and the volatile character of renewables requires also massive change in the load balancing. So in the former times it was very easy. We have the load on the one side and generation on the other, and the generation followed the load. In the future, this changes because renewables are fluctuating, and we have to. The demand side gains in importance, so we have to be flexible on the load side, on the demand side. Another challenge that results in the character of low voltage distribution grids in future energy flows must be actively managed. So we have to connect all the different consumers and generators and storage systems, which requires a lot of sensors and actors. And today, none of these are present in the low voltage grids. And electric mobility is particularly challenging in this respect because of the high power we are facing. Oh, sorry, I missed to click on the slides. Sorry. Yeah, these are the pictures for the slides I missed. Okay, sorry. Next slide. The challenges in the power grids, I try to list all the biggest challenges. On the right-hand side, we see the target triangle, and the challenge is to find the sweet spot inside that triangle between stability of security and security of the supply, the environmental sustainability of the system, and of course economics. So to find that spot, we have to minimize cost of transformation, we have to minimize the grid enhancements, we have to minimize congestion of generation and conversion losses. So the grid operation must go closer and closer to the capacity limits of existing grids to reduce the enhancements of new grid lines. And that requires like an active management of power flows. And that's not possible without automation and digitalization. So keeping all that in mind, how does the transformation of the transport sector looks like? how does smart charging infrastructure look like? Looking at the roadmap, we see different stages of evolution. The first one is state of the art today, maybe also yesterday. We are already maybe in the second phase, where we have not only grid compliant charging, but already going in the direction of controlled charging. So the charging can be controlled regarding power and schedule remotely by different actors like the system operators, grid operators, like charge point operators, like the users themselves, or like building management systems. The next phase then would be like bidirectional charging, energy transfers between the batteries and home or grids, and also grid services like energy transfers motivated by sustainability or economical reasons, self-consumption and stuff like that. And one of the following stage would then be even more automation, autonomous charging infrastructure automatically reacts on grid status, like sensing voltage and providing a reactive power, stuff like that. And the flexibility is automatically forecasted. Charging schedule adapts to grid services and energy markets. So that's like a roadmap. As I said, we are already in the second phase, heading to the third phase. And I have a couple of slides showing where we are today. So at the moment, we are working on the grid-friendly operation of electric vehicles. That is why, because we have to bring in more cars into existing grids, we have to bring in more renewables into the grids, and these two systems are really fitting together. So what does it mean, grid-friendly? In very basically spoken, it's reducing the peaks, the power peaks. So that's necessary also as well as for generation, as well as for consumption. And in this slide, we see what grid-friendly means in the field of solar generation. So that means buffering the solar peak at noon into storage systems, and these values measured here were formed with a static batteries, but we can also adapt these on electric vehicles. So we have to find the right moment to feed or to charge the cars, buffering the solar peak and bringing renewable power to the mobility sector. And this results also in reducing the necessity to enhance the grids. What we see here on the top right corner. So going to the next slide, we see that we have the charging itself is also very challenging for the grids. We see here on the bottom two measurements of charging process at a private home. The yellow curve is the solar generation curve, and the gray peak is the charging process with 20 kilowatt car, what is quite usual, and a quite big generation system of around 8 to 10 kilowatt peak. And we see that there's a significant peak for charging very shortly, but if we manage that peak, we can smooth it, we can just prolong the charging process, we get more solar power in the system, and we reduce the peak at the grid level. So that is the goal, what we are doing. What we need for that is flexibility information. We need to know how long the car is connected to the grid, when does the user needs the car for next time, when does it have to be fully charged. That is something what is at the moment is not automated very well. So the user has to type in this information in an app mostly, but this is in future should be quite automated, and the systems can then handle that flexibility and get more of the solar power in the system. What we face for problems or challenges in this respect, we had a lot of research projects in the last years in this direction, and we see here a curve where you see what happens if the prognosis fails, or if you have a lower forecast quality. In the middle, you see that the solar peak at 12 o'clock, for example, is low, but nevertheless it's charging. That was because the forecast was saying there's enough sun, and there was maybe a cloud or whatever, and the charging process was not adapted. And this can make things even worse if you rely on bad forecasts. So that's, sorry. This is the slide I explained. So, and what we did then is redeveloping or improving our charging algorithm, the charging optimizer. In this generation now, we are considering real-time values at the grid connection at the building. This is done by developing like decision policies, and on the other hand, getting real-time measurements at the grid connection point. And then this optimization considers all that and getting absolute much better performance in the end and higher PV rates. Okay. So this optimization of charging processes is highly dependent on the environment of the use case. And we had a number of research projects where we developed interfaces to the grid controller, allowing for congestion or limitation of charging power, for example. We had research projects where we developed interfaces to energy markets, allowing for cost-optimal charging and, for example, CO2-based pricing schemes. And we had interfaces to charging clusters, fleet management systems to optimize the number of cars, including maximum power monitoring and prioritization of cars. I have to speed up a little bit. So what's coming next? We look next years. Feeding back the energy from the cars into the grid is close to breakthrough. So application is very interesting for not only for PV own consumption, maximization and peak management, but also on the bigger level, pooling cars and for energy markets offering like grid services, control reserve and whatever. And state of today is in Asian markets, Asian standards. They are a little bit further than the European systems. In Europe, CCS models are not feeding back energy yet. But we are working on that, and many companies announced bringing models into the market this or next year, so we are excited about that. What we have to do there is quite a lot. Is communication protocols are not ready for doing that. The regulation and clearing are at least not standardized on an international level, so every country has its own regulation. And for example, in Germany, the regulation is not very attractive, making all business models difficult. So all these can be tested in our facilities, our digital grid lab, for example. So I have one minute left. Is that okay?
Yeah.
I'm heading. So okay. Last but not least, I would like to. Okay, thanks a lot. I saw the counter going to zero. But okay, last but not least, I would like to point out the role of power electronics. Because besides IT, so communication interfaces, control algorithms, artificial intelligence, what I did show here is power electronics is the key for successful grid integration. So basically, power electronic converts between the AC, which is common in electricity grids, and DC direct currents, so for the batteries and motors. And the efficiency of that conversion is critical, performance parameter, not even for solar industry, but also for every device in future. But the importance of power electronics in future power systems is much higher. So all rotating generation is replaced by power electronics, defining, forming grid operation. So power electronics and charging systems can therefore deliver data, services to the grid, supporting grid stability and efficiency. And we are solar research institutes. We are doing research on power electronics for 20, 30 years now. And we are bringing that experience now into also the transportation sector.
Thank you so much for your insights. That was Dr. Robert Kohrs from the Fraunhofer Institute of Solar Energy Systems.